Right. First of all, just about the lab test number 3, it will be next Tuesday and Thursday, right? Now, after the reading week flipped, so Tuesday session first for the lab test. If you go to the lectures page, I just uploaded a preparation guide. So if you go there, preparation guide, it tells you exactly what is covered, and then there are also preparation exercises I gave to you. I will release the solution on Monday. Before that, I would like you to try. Don't rely on my solution. Okay, I really want you to try. And the lab test itself, if you really have done the exercises on your own and you really understand what's going on, it should be straightforward. Okay. Okay, let's now cover a new topic, recursion. This is a hard topic. Okay, you are actually going to learn this again and again and again in 2011, 3101. So recursion is quite an important concept. To most of you, when you first see the recursion, you'll find it very, very weird. But it actually works magically, okay? But now I want to go to the last page of the lecture first. I want to point to you the references. So there are several references I want to point to you, and you really want to get started with some self-paced study. So we have some notes on the recursion. So this notes over here, just about 3 or 4 pages long. That summarizes all the 8 examples I'm going to cover in the slides. So read it over. It kind of cover in a little bit more formal way. If you're comfortable with mathematics, that one should really give you more insight into recursion. Okay? And the second one is we're going to talk about recursion on strings and arrays. So if you are not so familiar with the strings API, we'll cover a little bit today, but you should really go to the API and see that. Now, so here are 2 very great websites for you to learn recursion. I'll show you. So there are two over here. I believe 2 is more advanced than number 1. For example, if you go there, there's a website there. Just go to Java version here. They got lots of recursive problems there for you to solve. And the good thing is, for example, if you click on one of them, you try to program your solution, and then you can say go and submit. It's going to, under the hood, it's going to run some JUnit tests on your code and tell you how correct you are for your recursion, okay? I will encourage you to try all the problems for these 2 websites, okay? And now, this is not really mandatory for this course, but if you really want to learn recursion well, I would suggest you start self-study on some functional programming language, and the one I would really recommend is something called Haskell. And I do have some tutorial document here. You can just go over, and if you got any trouble, feel free to talk to me, okay? The last item is optional, but really for your best learning outcome for recursion, that's really the best approach, rather than Java. Java is not a very good language for learning recursion, okay? Okay, let's now start the topic about recursion. Okay, so what's really recursion? I want to just give you some general view, introduce some terms, and then we'll do examples. Okay, we'll have about 8 examples to go over. But today, hopefully we can go over at least 2 to 3, okay? So what's really the principle of recursion? Recursion is very useful in expressing solutions, like how you can implement your methods, especially for problems that can be defined recursively. But what do I mean by recursively? I want you to recall what you learned in high school or your first year mathematics about mathematical induction. Let's say I want to prove the following. Let's just go for some simple example. Let's say the following example over here. If I say the following property over here, I say P of n. So this simply means the sum of the first n integers from 1. So we know the formula very well, right? It's simply just 1 plus n times n divided by 2. We know that very well. It's basically just a very simple arithmetic sequence. Let's recall, how would you prove this by mathematical induction? How many cases do you have to prove? 2 cases, right? Which 2? Base and recursive, right? Or inductive case. Okay, let's just read very quickly. You will see that it's lots of reconnection there. So basically, something called base case. Base case simply means these are very trivial values that's small enough you have to make sure it's satisfied. For example, base cases can be P of 1 and P of 2. Okay, you can prove that very easy. Okay, and now what about recursive cases? Recursive or inductive? And inductive case over here. So from the programming point of view, I'm going to say recursive case rather than inductive. For inductive case, what do you do to prove that? You assume something, right? And then use your assumption to prove something else. Okay, let me just write it down. For example, you got to say assume. This is my inductive hypothesis. Assume P of n minus 1 is exactly equal to 1 plus n minus 1 multiply n minus 1 divided by 2, something like that, right? And then use this assumption here to prove P of n. And then you can do the derivation, right? So that's really what you do for mathematical induction. You will see that the way you program recursively, you got to follow almost identical procedures. Okay, that's why I really want you to draw your connection back to the mathematical induction. So let me highlight again. So these are really the important components. You cannot miss any one of them. First of all, base cases. And then you have to assume something. And then you have to somehow derive something. Okay, when I say proof, in the programming context, somehow you have to, I would say, derive. You got to do some massaging on your mathematical equation. Okay, these are the three components. Any question about mathematical induction? No? Okay. Now, let's talk about recursion in the programming context. Now, if I want to solve some problem recursively, again, I need to give two base cases. Okay. So the first case is base cases. So what are really the base cases? Base cases simply means that these are the problem instances. The problem size is so small, I can solve them right away. I don't need to hesitate. I can just solve it. Okay? And I'm going to give you one example from the second slide, but I think it's important to go through some concept. So base cases are things you don't have to hesitate, just give solution right away. And these, what about recursive cases? Recursive cases means these are actually bigger problem instances. The size is way too large for you to solve right away. What I can do is I simply say this is the solution I want for this particular strictly smaller problem instance. I assume it is going to work. I assume. That's really important. But of course, the assumption somehow can be guaranteed by the runtime system of Java. Okay? Now, I can take that assumption there and do certain combination with something else, and I can derive the solution overall. Okay, we'll see that in just a moment. Okay, so these are large problems which cannot be immediately solved. So we simply have to assume something that's strictly smaller. So strictly smaller is very important. Okay, we'll see why. Okay, and then. Okay, as I just said, this has some very much related to mathematical induction. What about in Java? Actually, not just in Java, in any programming language you might program in, they all got recursion supported. How can you see there is recursion in your program, either intentionally or by accident? Okay, let's see. In general, let's say you're trying to define a method called n. If somehow inside the body of the method n, you're trying to call itself, that means you're trying to do recursion. Okay? For example, let's say over here, you can see that we're defining method n, which takes some parameter I. You can see somewhere inside the body of m, we're trying to call m of another instance, right, over here. But now you can see I and j, let's say they're simply just integers. If I and j somehow are just the same, then that's not really proper recursion, right? Because we say that every time if you want to make a recursive call, you want to solve a smaller problem, strictly smaller. So over here, j here, oh, just blocked. Okay, j over here, the red one, somehow the value must be strictly smaller than the I over there, just in general. Okay. Any question about this slide, just about general concept, before I move on to our first example? Okay. Okay, first example is so-called hello world example for recursion. Okay, usually people talk about factorial first. Let's review what a factorial is. So factorial is, that's a notation here, n factorial. N can be starting from 0, and the n factorial, 0 factorial is simply just 1. If you got larger number, starting from 1, 2, 3, 4 until very large number, you simply just go from that number particularly and then decrements until it is 1, right? Just multiply them all together, right? This is factorial, okay? No question about this, right? So now, we want to somehow define this recursively, okay? the solution we have above over there, you can easily run a loop to do it, right? You can start it from 1 and then keep multiplying, keep accumulating, and then until you reach n, right? That's how you can do iteratively. You can do that easily. How do we solve this recursively? Let's try to think about it. Okay, let me just go back there. Let me try to illustrate exactly this problem over here, okay? So now let me just add a new page. Okay, now, so what we have is something like this. So let's say the problem we are trying to solve is n factorial. Okay, that's a problem. And we say that this over here is the size of the problem. The larger n is, the larger problem we are trying to solve, right? So now let's think about this. Let's just review the definition and then I'll give you some intuition. So we know that n factorial is simply equal to, if n is simply equal to just 0, that will be just 1. Otherwise, it's going to be n times n minus 1 times n minus 2, all the way to 1. And this is where n is larger than 0. Okay. Now, how can we solve this recursively? Let's deal with the simple cases first. Remember when we try to solve a problem here, and step number 1, what are the base cases? Well, 0 here, right? It's quite obvious, right? So base cases simply means you can solve it right away without any complex computation, right? Base cases, for example, we can say we can say 0 factorial is simply equal to 1. You can even say 1 factorial is equal to 1. That's not necessary, okay? Only this one is more. That's, as well, you should get at least one base case. Now, what about recursive cases? Let's try to see the problem over here. Let's say you want me to compute n factorial. Let's say here, you want me to compute n factorial over here, and n is guaranteed to be larger than 0. For example, let's say, let me give you a concrete example here. What is 5 factorial? First of all, I cannot solve this right away. I just cannot. It's too big. I only know how to solve 0 factorial or 1 factorial right away. That's the only thing I know. Those are the base cases. But let's get some insight. We know that eventually when you unwind the factorial, it's going to be 5 multiply 4 multiply 3 multiply 2 multiply 1, right? Now, let's try to see, just for this particular case, you can see 5 is simply just the n factorial we are trying to compute. I can get an n right away, right? If I want to get n factorial, I can get n directly. But what about the remaining part? If somehow you can identify this remaining part as the solution to the same problem, but a smaller problem, then that's recursion. Can you see this 4 times 3 times 2 times 1? Do you think it's kind of like a similar problem, but of a smaller scale, right? It's 4 factorial, right? So this part over here is simply 4 factorial. Similarly, I can also make the following claim. If I have, let's say, 7 factorial, what I can do is, I can say 7 right away, multiply by whatever 6 factorial is. Because, well, I know just from that example there, right? Any question until now, just for these 2 examples? Okay. What about in general? In general, you can see that over here, this part over here, after n, when you go from n minus 1, n minus 2, all the way to down to 1, that would be simply n minus 1 factorial. You can see the problem we are trying to solve over here is really factorial. You can see the factorial is really the problem. And you can see the original problem size was simply just n over here, but now we cannot reduce that into n minus 1. Okay, let me just rewrite that definition there. So we say that n factorial is simply equal to n multiplied by n minus 1 factorial. Any question until now? I'm going to see some code in just a moment, right? Okay. So now let's finish this remaining step. So we got base cases. We also got recursive cases. Recursive cases. What we can assume is, let's assume we have the following. Let's say we assume we have n minus 1 factorial already. We don't have to compute ourselves. We delegate that to somebody else. Okay? We just don't have to do it by ourselves. And let's just annotate what this is. n minus 1 factorial is basically the solution to a strictly smaller problem. Okay, just that one. Let's assume we have it. And then we can take this assumption here and combine that with something else and make the final solution. So now what we can have now, and then we derive the following. This is the original problem we want to solve, and this is what we assume we have. And then we can say simply multiply by n. Okay? Okay, let me just annotate this again. So this is the original problem. And this one here is a subproblem. And this one here, we can easily get it. Okay? So now, let me just review very quickly. We got base cases there. 0 factorial is 1. 1 factorial is also 1. For those cases, we don't have to delegate any further. On the other hand, for the recursive cases, we got 2 sub-steps. First of all, we have to assume we have solutions to subproblems. In this case, just one subproblem, which is n minus 1 factorial. n minus 1 is strictly smaller than n, so it's a smaller problem. And then we say that given this n minus 1 factorial, we can combine that with something else. And then after this combined solution here is equal to the ultimate solution we want to find. Okay? Any questions until now for this? And then we'll see some code and try to trace. Okay? You will see that this kind of pattern applies for every problem that we're going to solve. Okay? So this is the very first one. So I'm going to repeat the same pattern over and over again. Okay, let's now see how we can define this in Java. Okay? First of all, let's see the recursive definition. We simply say that if n is equal to 0, then we have 1. Otherwise, it's n multiply n minus 1 factorial, right? Just as we said. Now, let's see how we can define factorial method in Java. And then let's try to trace it, okay, in just a moment. Let's say we have a method called factorial which takes integer n. Now, again, the body of the method is exactly corresponding to the 2 parts we talked about, base cases and recursive cases. Okay? Now, what about base cases? We can say if n is equal to 0, then just return 1. It's pretty much like a P0, P1, right? Something like that. What about recursive cases? Otherwise, we know that n is strictly greater than 0. In this case, we assume we have something called factorial minus n minus 1. You can see n minus 1 is strictly smaller than n over here. So that's the solution to a strictly smaller problem, right? And if we can get a value for that, we combine that with the n that we are talking about over here. And then multiply them together. The combined solution there is the ultimate solution we want to get. And then we just return it. Any question about so far? Just as, well, that compiles, of course. So if you download the source code for on the website, so I got the everything there, so you can also feel free to try. Okay, let's now try to, yeah.
What if I do it, I know you said like it's not necessarily to one, but have like an else does that matter?
It wouldn't really matter in terms of efficiency, it wouldn't matter, yeah. So the question was, if you try to add a new base case, let's say if n is equal to 0, return 1. Else if n is equal to 1, and then return 1, and then else do the same as before. So you just saving 1, basically recursive call. That wouldn't make a huge difference. Yeah, that was a good question. Okay, let's see how we can trace this. Okay, let's try. I'm going to show you different kind of tracing it. So there are 2 ways to trace this. We can do it from the more abstract level, like a tree. And then the second way of tracing it, we're going to use one of the data structure you just learned on Tuesday, stack. Okay? I will show you the abstract way first. That one is much more intuitive. However, you're also required to know how to trace using a stack. I will do that only for the first 2 examples, and then I'll assume you know how to do it. Okay? Let's now try the abstract way. How do we trace? Now let's now go to, so this is factorial code. Okay? Now let's try to trace it from using two different manners. So let's say tracing. Let's say we want to do factorial. Let's say 4 over here, right? How do we trace that? Now let's try this. If I want to compute factorial 4, is this the base case? No. So I cannot compute that right away. I need to delegate that further. Okay? So that means I cannot do that. Let's hold it. Okay? Factorial 4 should be equivalent to, okay, let me just draw it this way. That's a little bit better. It's going to be 4 multiply factorial 3. Right? Now, is factorial 3, guys, do I have to mention that no talking in the class every time? Okay. Now, how do we know if factorial 3 is the base case or not? You can see the condition for base case is n is equal to 0, right? 3 is not 0, so we are not done yet. So we're going to move further. So now what about factorial 3? So it's going to be, by definition, 3 multiply factorial 2, okay? And we are not done yet, not yet. So we're going to hold it. You can see so far, you can see the original problem we wanted to solve was factorial 4. But we couldn't do it right away, so we hold it, okay? To do that, we got to also calculate factorial 3, but we also hold it because we got to calculate factorial 2 first. Let's now continue further. And this is going to be 2 times factorial 1, okay? According to our code, factorial 1 also is not a base case, so we have to go a little bit further, right? So now I don't necessarily have space, but I'll try. Okay, over here, you can see that this guy here over here is going to be, I'll just put it here. It's going to be 1 multiply factorial number 0. Now, what about factorial 0? You can see, now n is equal to 0, so we have this exactly this base case over here, right? So that means that one is going to be 1. So now let's try to go back, in the reverse order, right? So you can see factorial 4 was the very first one that was put on hold, and then factorial 3, 2, 1, and now when we try to compute, we'll see that the way we return is going to go the reverse order, right? So now factorial 0 is going to return, let me use a different color here, it's going to return just 1. So at the bottom level, now we can try to go back. So now we got 1 multiplied by 1. By doing this calculation, we know 1 times 1 is a result for factorial 1. Okay? And then, what about factorial 2? We used to be not able to calculate factorial 2 because we were waiting for the result for factorial 1. But now it's available. So now we can say 2 times 1, which is 2. So 2 is the result for factorial 2. Now, we can also calculate factorial 3 because now we got a result for factorial 2. So 3 times 2 is 6. And then 4 times 6, 24. So 24 is the final result for factorial 4. Okay? Any questions before I make some observation for you? Any questions? Okay, are we okay? Yes?
So the complexity will be the same as doing the forward, right?
Yes, but somehow the solution, yeah, I agree. So yes, in this case, yes.
Okay.
Yes, complexity will be the same because somehow you can see that the height of the tree, wow, we haven't talked about tree yet. The number of recursive call you're making here correspond to the number of times you got to decrement n until 1, right? Right, that's exactly n, yeah. Okay, now I want to draw your attention to, you can see that, let me try to give some intuition. This will lead us to how we can trace by using a stack. You can see that our initial goal is to calculate factorial 4. In order to do that, we got to calculate factorial 3. And to do that, we got to calculate factorial 2. And to do that, we got to calculate factorial 1. And then we also got to do factorial 0. And that's exactly the stack structure that we talked about on Tuesday, right? You can see factorial 4 was the very first one that's put into the stack. That's the ultimate goal. But to do that, we have to go all the way. We've got to stack up the stack until we reach some base case so we can start popping off the stack. So now when we reach factorial 0 over here, we know that this guy here is simply just 1. Right? Again, we can keep going until we reach the final result. Any question about this kind of observation here? And then I will show you exactly how you can use a stack to trace it. Okay? Questions? Yes? Yeah. What do we put? Yeah, I will just talk about it in just a moment. Okay. So the question was, so what exactly do we put onto the stack? So the exact detail, you will learn about it possibly in the operating system course, but it's something called activation record or activation frame. So the way I draw it, you can see I simply put factorial 4. What does that mean? We are putting the information about calling this particular method with input argument 4. Right? That's conceptually what it is doing. Because eventually we still have to return back to this point here and then calculate. And this particular record over here tells us once you get a factorial 3 result, you're going to combine that and then multiply by 4. Right? That's kind of the information we store. But the exact detail, you don't have to worry too much. That's not the focus. Okay? We do have one slide to tell you very briefly what a stack frame is, but we'll go over that, and then I will show you how you can trace the recursive method using stack. It's actually quite important. Okay? Okay, so any questions about recursion here? Okay? This is our very first example, so I'll go very slowly. Okay? If you got questions. Okay, that's exactly the tree, the order of calling the method, and then until we actually reach the base case factorial 0, and then we keep returning. Okay? And then let me just go over some concept here. Okay, this one you can just read it over. Okay, and then I'll show you. Okay, so now every time when you're trying to do some computation, let's say factorial 5, let's say if somehow the method call is too difficult or too large for you to do it right away, what you do is you put it on hold. You suspend it. Okay, and that's why I put suspend here. So we're gonna something called activate and something called suspend. Activate means I'm going to start executing this particular method. Suspend means put it on hold and do it later. Okay. So now it's something called activation record. That's exactly what we put onto the stack, and also activation frame, whichever name you like. And then what do we store over there? So typically, you simply store anything that's relevant to this particular method call. For example, if I say I want to put factorial 5 onto the stack, I'm going to store about, okay, the argument value is 5, and so definition for factorial is that method I have, on the slides, right? Things like that. And then every time when you try to call some helper method or try to make a recursive call, you just stack up the stack, even further. Okay? Okay, that's just about the activation record, and then I'll now show you how you can do it using a stack. Okay, we got to use a stack. Now, let's see some principle over here. Let's go over the principle, and then I'll show you example. Okay, how do you trace the recursion using a stack? So this one pretty much corresponds to what really happened at the runtime, right? So when you execute recursion in Java or any other language, you don't really see a stack. It's done under the hood. But now we're just trying to show you how it is done. Okay, now every time when you call a method, let's say factorial 5, it is going to be activated, which means now we start executing it. It's going to be pushed onto the stack. Okay, and let's say inside the method, if you're trying to call something else, for example, if we say factorial 5, it is going to call factorial 4 inside, right? In that case, factorial 5 will be suspended temporarily, and then factorial 4 will be stacked up onto the stack. Okay? So that's when you push even more. And then let's say every time you got to look at the top of the stack. The top of the stack means this is the current point of execution. That's where we should go to execute some code. And then when we actually finish executing the whole body of a particular method, we're going to pop it off from the stack, which means it's done. Okay? For example, when factorial 0 is simply the base case, we just return 1. That means we are done. We can pop it off from the stack. Okay? And then every time when you pop off the stack, the new top becomes the new point of execution that you're going to continue. Okay? Let's see an example. And one more thing. So when does it really mean that you can stop your program. That means when the step becomes empty, nothing to be executed anymore. Okay? Let's see how we can trace this for the factorial. Okay? Let's see that. Let me just have a new page over here. And then I'll have the same code. Okay, over here, factorial. Okay, let me make it a little bit smaller. Okay, let's try this. Let's try to trace factorial 4. Okay, let's make it a little bit easier. Okay, you get the idea. Let me be a little bit lazy. Factorial 3, let's say. Let's say tracing factorial 3. I'll say fact over here rather than factorial. How do we trace that? First of all, step number 1, we're going to activate this particular method call, which is factorial 3. And then push factorial 3 onto the stack. So that means, let's say this is a stack that we are having over here. And we simply put factorial 3 inside. Okay? So this is the current point of execution, right? So now, let's try to execute 3. So now, let me just try to use different color to show you. Let's say, we talk about green over here. So now, it was one thing to note. Even though we are trying to call the same method many times, every time when we're trying to make a recursive call, it's the same definition of factorial that we are calling. Okay, I'm going to show you. When we have factorial 3, that means n is going to be replaced by 3. And then we know that 3 is not equal to 0. So that means result is equal to 3 multiply 3 minus 1, which is 2. Okay, that's what we know. Right? So now we know that when we push, and now we're going to execute. Execute factorial 3, which will give to us 3 multiply factorial 2. Okay? So now, 3 here is not any method call we are making. Only factorial 2. That's just another method call, right? So now what do? We're going to activate it. Okay? So now, what we're going to do in the next step, we're going to say activate factorial 2. Activate that, which means, and then push. And we're going to push that onto the stack. Push factorial 2 onto the stack. Okay? Now you can see that factorial 3 has been suspended. So we're going to do it later until we get some result for factorial 2. Now for factorial 2, what do? We're going to execute it, right? So because now it's the top of the stack. So now let's go to number 4. Number 4. Let's say we try to execute factorial 2. Okay, so now what do? We're going to call the same method with a different input parameter, different input arguments. So now it's going to be 2, the blue one. And then now 2 is not equal to 0, so we go to the else part. And then we have 2 multiply factorial 1. Agree? Good. And now, so what we have is, this is going to be unwinded into 2 multiply factorial 1. Now, what do we do next? Can you take a guess? Should we activate something? Factorial 1, right? Because now we know that before we can make a conclusion about what factorial 2 is, we have to know what factorial 1 is. That's why I'm going to activate it first. Okay? So now let's use it again, a different color. Number 5, you're going to activate factorial number 1. Okay? Factorial number 1. And then factorial 1 is going to be pushed onto the stack. And then you will say push factorial 1 onto the stack. Okay, we're getting there. We're really getting there. And then we can say that, now let's try to execute factorial 1. Then execute factorial 1. So what's going to happen? If you do that, you know that n is now going to be 1, right? So now we're calling the same method a third time with the different input variables. And every time you can see the input size has been strictly decremented, right? It's strictly smaller. So now we have 1 is not equal to 0. Still go to the else part. So now we got 1 multiply factorial 0. Okay? So what we get is 1 multiply factorial 0 over there. Okay? And then, now what next? Should we do any further activation? We should, right? Factorial 0, exactly. You can see how tedious it is to trace it, but I think it's really important to know. We wouldn't put this on the test, but it's good to know, right? Okay, let's try this. And then we got number 7 over here. How about pink? Number 7 over here. Let's say we try to activate factorial 0. Even if you know that it's a base case, but activate it first before you can find it out. So activate factorial 0 and then push onto the stack. Push factorial 0 onto the stack. So now we got factorial 0. And let's execute it, right? It's now the top, so now the execution point will start from there. So now if that's 0 there, so you can see that we have 0 over here. In this case, what do we do? It's a different case, right? 0 equals 0, true. So we're going to result is equal to 1, and then skip the else part and simply just return 1. Agree? Okay, good. So now let's just do the following to save some space. So now let's go to, let me use some color which I haven't used. Let's say gray. Now number 8. So now factorial 0 returns, simply returns 1, and then pop the stack. Okay, so this one over here simply returns 1. Okay, that means once we return, you can see this part over here can be replaced by just 1. Right? That's what we have been waiting for. Okay, so once we have done that, so now you can see factorial 1. So that means factorial 1 is exactly equal to 1 multiplied by 1, which is 1. Okay? Now, what about number 9? Number 9 over there is going to be factorial 1. It's going to return something, right? So now, because now factorial 1 is now being the top of the stack. So now, the one we were holding was factorial 1 over here. That's what we're waiting for in order to calculate factorial 2. So now we know that factorial 1 is simply just 1. So now we can calculate, and we know that factorial 2, okay, factorial, and then pop, right? Yeah, I'm sorry, I'm skipping too many steps. And then we'll simply return, but I kind of get the idea. Returns 1, and then pop, right? That's why you get 1 over here, and now you know that number 10. Factorial 2 is 2 times 1, right? It's going to return 2, okay? Returns, okay, I'm going to separate this over here. Returns 2. It's getting a little bit messy over here, but hopefully you're following the point, okay? So now factorial 2 is actually returning 2 over here, and now we can calculate factorial 3, right? Factorial 3 is going to be 3 times 2, which is 6. And then, I don't have space. What about 11 over here? Okay, 11 here. Factorial, so factorial 2 returns simply just 6. And then what about factorial 3 over here, right? So factorial 3 returns over here, this expression over here, which is 3 times 2. That would be 6. Returns 6. And then once it's returned, it's popped off from the stack, and stack becomes empty, and we're done. Okay? Well, that's a complete tracing of the whole routine. You can see it's only for factorial 3, right? My point is, let's try not to lose the big picture. You can see it's quite tedious, error-prone to do. But my point is, you can see that for this stack over here, we keep pushing when we cannot figure out a solution right away, right? Until we reach the point that the method can return because the problem size is small enough. So we can return the value and apply the definition. Okay? Yes?
Just clarify, remember that is still pop.
Yeah. Okay, let me just make it clear. Also gonna pop. Yes. Because remember, eventually, what does it mean when your program terminates? That means the stack is empty. Right? Good. Guys, any question about this? Okay. Okay, then we are fine. So now, let's see how we can. So that's about factorial example there. So if no question, I'm going to move on to the second example. Okay. I'm hoping to get through at least 3. Okay, today. Okay, I'm hoping you can digest and over the weekend, and then we'll see more challenging example next Tuesday. Okay, let's think about Fibonacci numbers. That should be quite familiar to you since we talk about Fibonacci sequence. Let's see the definition for Fibonacci number. The definition you have known about is already recursive. Let's see why. Okay, and we're gonna trace again. Okay. Okay, let's say we say Fibonacci n. So f of n is actually the problem we are trying to solve, and the size is just n. If the size is only 1, we can solve it right away. It's simply just 1. If the size is 2, then we can also solve it right away, also 1. So these are the 2 base cases. Okay? Now, how do we define the recursive cases? The recursive cases means if I want to solve f of n in general, I cannot solve it right away. Is it possible for me to assume some smaller problems actually got solutions already, and then I can combine them together, right? Since I got f of n being the problem I'm trying to solve, what would be the smaller problem? It can be f of n minus 1, n minus 2, n minus 3, right? So you shouldn't be too surprised to see something like this, right? So we are saying that in order for you to solve f of n, you can simply just combine the solutions of f of n minus 1 and f of n minus 2. Okay? Let's try to trace this right away, conceptually. Yeah? Okay. I'll try to answer. Okay, let me try. Okay. I'll try to answer you. The question was, why was that definition there, right? Okay. So let's think about what's a Fibonacci sequence, right? You got 1, okay, I'll say Fibonacci sequence, right? 1, 1, 2, 3, and then 5, etc., right? Right, etc., yeah, just keep going, right? So now, this is position number 1. We don't say position 0. 0, when you have a sequence starting with 0 in there, that's for programming, but now we talk about math, right? So this is F1, this is F2, okay? And the way we figure out F3 is already too big for us to solve. So what we can do is try to find out the solution for F2 and find out the solution for F1, add them up together. In this case, both are base cases, so we can just do it. Okay? So in this case, that's simply F1 plus F2, right? Maybe that answers your question, I guess? Good. Good. Okay, let's use this, page over here. Let's try to trace. Let's try to do the following. Let me just remind you about the definition over here. Fn is simply 1 if n is equal to 1, and then 1 if n is equal to 2. And also, it's going to be f of n minus 1 plus n minus 2 when n is greater than 2. Okay, let me do some annotation here. You can think of these two expressions here individually represent the solution to a strictly smaller problem, right? So this is the solution to a strictly smaller problem. And this is just the same, okay? Also, solution to smaller problem. And what we're assuming is we have the solution for f n minus 1. And we have solution for f n minus 2. If you do have them, how do you combine them together? That's how you combine, just add them up together. Okay. Let's see how we can trace it. We'll see the tree structured over there. Okay, let's see that. So now let's say we want to do f5. Okay, we cannot solve f5 right away. So what do? We have to somehow to say, well, it should be f4 plus f3. Now the order of evaluation is going to be from left to right. Okay, so now we're going to do f4. How do we calculate f4? It's going to be basically f3 plus f2, because f4 is also too large. Okay, so now before we can calculate f4, we got to calculate f3 and f2. Now what about f3 over here? It's going to be f2 plus f1. And over here, f2, is it too large or good enough? Too large, right? Because we are still, oh, actually it's okay. Sorry about that. Good, very good. So now, basically you can see now, f3 is too large to solve, but once we go by the definition, f2 is okay. So now let me replace that. It's going to return just 1. This one is also 1. Okay? And 1 plus 1, we can replace this by 2. Okay? And now what's left? f2. What's f2? Too large. That's also 1. Sorry, sorry, I'm tired. 1 over here. Not physically tired, mentally tired with tracing this. Right? Okay, now, how do we count? So now we got f3 and we got f2. So now we can add it up together to make the solution for the larger problem. So 2 plus 1, we get 3 over here. Now, is f3 too large? It is, exactly, good. Now, f3, we're going to do something very similar. So f3 is going to be f2 plus f1 over here. And then, is f2 too large? No, it's okay. We can definitely return. It's going to return 1. What about f1? That's fine. We can also return 1. And then, 1 plus 1, we have 2. Now, what's next? You can see that f4 has been calculated, which is 3. f3 has been calculated, which is 2. Combine them together, we can get a solution for f5, which is 5. Question? Yes. It's a very good question. Yes, maybe in reality, maybe that's how the compiler tried to optimize the recursion tree. But conceptually, you can think of, that's a very good question. The question was, you made a very good observation over here. Let me just make it explicit, okay? The question was, because we can identify, actually we're going to talk about this kind of tree next, maybe not next week, maybe the week after we're going to talk about binary tree, okay? You can see that over here we are trying to calculate f3 over here, right? Over here we're also trying to calculate f3. You can see that this particular tree structure over here is identical to this tree over here. Since we already calculated f3 being 2, why can we not reuse over here? You're talking about optimization of the code, which is left by the compiler. But conceptually, you should know that's how you trace. Yeah, very good question. Guys, any questions? Any questions? Fibonacci. I haven't showed the Java code yet, actually. Yes. What's the order of calculation? Good. The question was, what's the order of calculation? Let me show you this. How about this? Let me try to trace just partially using the stack, and then you will see. How about that? Okay. Let's try to trace. Let me show you the Java code, and then we'll trace. Okay. I'll hold that question in just a moment. Okay, that's the mathematical definition, recursive definition there. How do we do this in Java? You'll be amazed how easy it is. Think of, you're going to say there's a method called Fibonacci. And then it's going to take an integer. And then we're simply making 2 recursive calls, 1 and 1, right? Just 2 recursive calls. Let's see that. Let's say we call fib over here, which takes an integer, which can be 0, 1, 2, 3, 4, etc., right? Let's assume negative is not possible. Let's assume. Now, over here, we say that the base case, if n is equal to 1, just return 1. If n is equal to 2, return 1. You can see these two lines correspond to exactly the first two equations here in the definition, right? Now, how do we do this one over here? How do you do that? Well, make a recursive call, right? How many recursive calls are you going to make? Good, very good. Yeah, exactly. You can see we're calling the same Fibonacci method here, but one with n minus 1, the other one with n minus 2. One thing to know, you can see that always when we are making a recursive call, you should always pass an argument that's strictly smaller. What if it's just the same? Let me show you. Yeah, Ken, say that first, and that will illustrate. It's going to be infinite loop. Yeah? Yeah, it will until your computer got eaten up by its resources, right? So now, let's say how we can do this, okay? Let me just, this is an aside, but which is very important. Can we just go back to the factorial example? I want to show you something that's very important. Okay, let's go to the factorial, which is here. Let me modify the definition just a little bit, okay? Just a little bit. So this is a correct definition. Let's say I modify so that this part here, oh, actually I can do this, right? Can I? No, I cannot, sorry. I thought I can just use an eraser. Really? No, actually, never mind. White ink? Okay, I can try. Oh, that's good. That's good. Okay, never mind. Never mind. Yeah, I'm gonna practice it. Yeah, actually, never mind. Okay, let's say this is easier. What about I simply put n here? Okay, what's gonna happen here? You can see that what's wrong with this conceptually. This is to say, if I want to calculate factorial 5, I'm gonna assume factorial 5 is already there. That doesn't make sense. That's not responsible. You can only assume something that's strictly smaller exists, but not something that's equivalence. Okay? Let's try to trace this conceptually. What does that mean? Oh, actually, so of course, I got to modify accordingly. So this is not simply not there. I'm saying that factorial n, if n is equal to 0, return 1. Otherwise, just give me factorial n. That's what it is saying. Well, why don't we try? Now, what's going to happen if I say factorial 5? 5 is not the base case, right? So that means give me factorial 5. And then go again. 5 is not the base case. Give me factorial 5. You can still keep going until your computer dies. You can try that. You can try that. I don't want to try on my computer, but you can try. Okay, so that's a very important thing to note. Every time when you're making a recursive call, it has to be a strictly smaller problem. So you can see today we're mainly going to see we are passing integer. So the integer must be strictly smaller. And we'll see that next week you can do recursion on array. So what does it really mean when you want to make a recursion on array? That means the range of the elements you're considering must be much smaller, must be strictly smaller. But we'll get there next week, okay? Let's get the basic done. Okay, so now let's see the code over here, Fibonacci number, okay? So that's how you define Fibonacci number here. And now go back to your question there, what's the order of evaluation? Let's see. Let me just say something here. You can see that in the recursive case, we are making two recursive calls. What's going to be the order of figuring out what Fibonacci n-1 is and n-2 is? It's going to be, the principle is easy, from left to right, which means before I can figure out what Fibonacci n-1 is, Fibonacci n-2 is going to be suspended. It's going to be actually not even suspended, it's going to wait, okay? After I can figure out what Fibonacci number n-1 is, I'm going to go ahead and push Fibonacci n-2 onto the stack. Okay? Let's see that in some small example. Okay? You can feel free to go over the example for Fibonacci 5. That one is quite a long trace. I don't want to bore you in the class. I want to do just a very simple one here. Feel free to go over. Okay? I wouldn't put this on the test, don't worry, but it's for your knowledge. Okay? But let's now try something very simple just to illustrate the idea. Okay? Let's try something that is not the base case. Okay? That will make sense. Let's say we have Fibonacci over here. Why don't we try let's say Fibonacci of 3. 3 is definitely not a base case. It's neither 1 nor 2. Okay, so what do we do? So now you can see that, let's try to trace. The step number 1. So remember this is the stack over here. So we'll say activate Fibonacci 3. And then you push the corresponding activation record onto the stack. And then you will say push Fibonacci 3 onto the stack. So what you get is Fibonacci 3 over here. Right? So you're going to call that. Because this is now the top of the stack. So the current execution is going to go from there. So now you have 3 over here. And 3 is not equal to 1, not equal to 2. So you're going to say result is equal to Fibonacci 2 plus Fibonacci 1. Okay? Okay, and then we'll say, okay, execute. We'll say execute top of stack, which is Fibonacci 3, right? Now we know that by definition it's going to be Fibonacci 2 plus Fibonacci 1. In the case of the factorial, we didn't have this situation because we simply say n multiply factorial n minus 1, only one recursive call. But this one we got 2, right? So now back to the original question there, what should be the order of evaluation? The principle is from left to right. We're going to figure out what Fibonacci 2 is before we bother to evaluate Fibonacci 1, left to right. Okay? So now let's see how we can continue. So we're going to say activate. Let me just use some color here. So this one is left. Okay? So we're going to activate Fibonacci 2 and then push. So you got Fibonacci 2 over here. And what's Fibonacci 2? In this case, you have 2 over here, and 2 is indeed the base case. It's going to return 1. Okay? Execute Fibonacci 2, and that one is going to return simply just 1. Okay, let me just separate that over here. So this one is going to return 1, and then we pop. Okay? Return 1, and then we pop. Now what else? You can see now, after Fibonacci 2 is popped, what's now the top? Fibonacci 3 again. So now we can continue from there. What does that mean? We used to just figure out what Fibonacci 2 is. So this guy here is still waiting. So now it's his turn. Okay? So now we're going to number 5, activate Fibonacci 1 over here, and then push onto the stack. Okay? It's going to be Fibonacci 1. Okay? So now number 6, let's be complete. Number 6, we're going to execute Fibonacci 1. And we know that if you have 1 here, 1 is exactly equal to 1 over here, the base case, the first base case. So it's going to return 1. So we know that it's going to return 1 and then pop, which return 1 and then we pop. Now, after we pop, what else? What then? Well, you can see that after it's a pop, now the top is Fibonacci 3 again. So now that means we are basically at the end of this point over here, right? So now Fibonacci 2, we know that it's simply just 1. Fibonacci 1 is also 1. So we got 1 plus 1. So we know that now number 7, execute Fibonacci 3 again, because now we know that Fibonacci 2 is 1, Fibonacci 1 is 1. So now we got return 1 plus 1, which is simply just 2. And then we pop. And then after we pop this one, it now becomes empty again, so we terminate. Okay? So now you can imagine how complicated to trace Fibonacci 5. That's why it occupied the whole slides. I'll leave that to you. Okay? Any question about this before I move on? We might be able to do better than I thought. Right? We can do maybe 2 interesting examples. 2. Okay? Guys, any questions before I move on? So from now on, I'm not going to use a stack to trace a recursion anymore. Because the thing is, once you understand what it is supposed to be traced, you don't have to repeat it every time by yourself. It's too tedious, and also it's too time consuming. But you got to know at least how to do it. Okay? So now, the way I'm going to trace for the rest of the the lecture on recursion is by using just a tree structure, right? It's much intuitive, okay? Okay, let's now go to our next example. Okay, now I want to just make sure you understand some methods on the string, because we're going to do recursion on strings, also recursion on array. Let's do string first. There is certain method I want you to make sure you understand how they work. Okay? Now, so first of all, you know that in the string library, this is empty. Oh, sorry, not this one here. There is a method called isEmpty, just to check if the string is empty, right? That's why it's easy. So typically, the base case, let's say I want to run recursion on this string. Typically, the base case is simply if the string is empty, okay? Pretty much like when you reach 1 or 0 for the numbers, right? Similar idea. Now, I want to draw your attention to a substring, okay? This one's interesting. It might be a little bit counterintuitive, okay? Let me just give you one example to show you, okay? Now, let's say, let me just give you one example here. If I say string, let's say S is York. Think of string as an array of characters, starting from index 0, okay? Now, when I say another string, S2, is simply assigned to, let's say, S dot substring. Now I say 0 and then 3. What should S2 be? Should that be York? York without cur, right? Okay, just make sure you understand that. Okay, first of all, the S2 is going to be just YOR, 0, 1, and 2. Exactly, that's exactly what I'm going to explain. So, so you basically go from 0, 1, and 2. So that'll be YOR. Oh, if you go 0, 0, that means it's just empty, right? Okay, I see what Kenneth was worried about. Okay, let's see this. First of all, let's make it a little bit formal here. When you say substring, S dot substring over here, in general, if you put some index I1 and, let me just use maybe a little bit better. Let's say I and J. It's going to combine all the characters in this range. I, open, J, closed. Okay? So that's why when you say substring 0 and 3, it's going to get character 0, character 1, and character 2. 3 is excluded. Okay? That's something a little bit tricky. Okay? I'll show you one property to illustrate this. That will help. Now, what about this special case over here, 0, 0? That's as if you do from 0 until -1. So this simply means empty, just no string. Okay? Now, I want to show you one property over here, if that makes sense to you. I hope that will help. Now, let's try the following. If I given any string, anything. If I say S dot substring 0 to I over here plus S dot substring I, and then I can say S dot length -1. What is that? Let's assume that I is a valid index, right? So let's assume. So where I 0 less than or equal to I less than S dot length -1. That's our assumption, okay? Like that. So now what's that equal to? S dot substring from 0 to I, and then from I to the S dot length -1. Yeah, just equal to S itself. Let's illustrate that. That's exactly the point. Let's try York. If I say, let's say this is S dot substring from 0, let's say I is 2. How about that? 0 to 2 plus S dot substring. Okay. Oh, actually, you know what? This over here, I think this should be the length, right? Yeah. Oh, yeah, I just realized that. Very good. Hopefully you agree. Okay, let's see how that works, okay? And then S the substring. And then we have also 2 here. And then S the length, which is 4. Agree? So S the length is simply equal to 4. Oh, I'll just put 4 here. Okay, so now what does that mean? So now this part over here is basically going to give me characters at position 0 and position 1, which is going to be YO. And then this one here is going to be the characters at position 2, position 3, position 2 and position 3. And that's going to be R and K. And then add them up together, you get York. Okay, I hope it's not too tricky, right? My point is the second index there is exclusive. You will see that quite a lot, okay? Just make sure you understand that, okay? Questions about this before we move on to recursion on strings? Okay, let's try this. Palindrome. Do you know what a palindrome is? A race car, yes, that's exactly one of the examples I have, right? What's a palindrome? A palindrome is simply a string which reads backward and forwards the same way. Well, it's the same. For example, let's say, what about empty string? Is empty string a palindrome? It is, right? What, read forward, backward the same? Yes. What about a single character? Good. Madam? Good. Race car? Yeah, right? Right? Man. Is man or nan? Nam, right? It's not the same. Okay, you get an idea. Now, first of all, actually, you know what? You got different way. Now you got 3 possible ways to solve this problem here. You can either use a loop, which I'm pretty sure you know how to do it. Let's save that for later, okay? Now, you can also use a stack. Think about how you can use a stack to check if a string is a palindrome. I'll leave that to you. Now, how can we solve this problem recursively? How can we do that? Let's try to sketch some idea. You know, the recursion, I tell you what, when you are given a recursive task to solve, don't try to dive into programming right away. That's not the right way to go. You should really try to sketch some idea on the paper, which I will show you. And once you get the idea clarified, translating it to Java is straightforward. Okay? The Java syntax is not the main issue here. Okay, let's try this palindrome. Huh? Oh, no, it's okay. I'm gonna illustrate that. Yeah. If you got it, don't say anything. Okay. Yeah. Unless every one of you got it. No, I don't think that's the case. Okay. Let's see palindrome. Now let's see this. Let's say I have a word over here. Let's race car. Let's say I'm given this word over here. How do I tell if that's a palindrome? The palindrome means it reads forward and backward the same, right? So what I need to do is I need to somehow figure out. First of all, let's figure out what the base case is. How about that? Base cases. Base case. Say it again. Yeah. You know, when you talk about base case, talk about the string itself. What would be the string that's so trivial for me to solve? Okay, there's empty or 1 character. Base case is empty string is palindrome. If a single character is also a palindrome, right? That's easy to check. You can check the length of the string. What about recursive cases? Now, recursive cases working a little bit like that. Think about this. Somehow I want to break this string here to some smaller string. If somehow I can say that I can give a smaller problem to somebody else, and then I can just keep the rest. Once they give to me their solution, I can combine them together, right? So now, what's really so special about the palindrome, the word here? Let me give you a visual hint to see if you get it. So what does that mean? The first and last character. So that means if a word is a palindrome, that means the first character and the last character must be the same. If they are not the same, there's no way it is palindrome, no way. Because it already, if you read it forward, backward, it's already different from the very first character, right? That means if somehow I know that the first and second character are the same, there is a chance it is a palindrome. There's a chance, not necessarily the case. Okay? So now let's say this. I know that for this particular string here, these two are the same. Now I can go on to solve a smaller problem over here. The smaller problem is take out the first, take out the last, take a substring, which will be ACECA. It's a strictly smaller string. Now, too large for me to solve. I can somehow to say, compare the first, compare the last. They're the same, so now I do bother to really check out later, or check out further. And then I just take a substring in the middle over here, which is CEC, right? Again, check the first, check the last. Over here and over here, they're the same, right? And now, the only thing I got left is a single character, which is base case, right? Let me give you one case where it is not palindrome. Let's see how we can do it, okay? Now, let's see one case over here. Race bar, for example. I'm not sure what that means, but whatever. Okay, let's see why it is not. Okay, let's try to work a little bit algorithmically. So over here, let's see this. First of all, we know that R matches R. There's a chance. So we go to the middle section here, and we know that A matches A. We still have a chance. But now we see that C does not match B. So we don't have to bother go any further. Okay, so now we are done. It's not a palindrome. Okay, so now what does that mean? That means every time if you want to check if a string, a long string is actually a palindrome, this is what you do. Check if the first character and the last character are the same. If they are the same, you can go on to make a recursive call on a substring of that. Then the substring is exactly equal to the string taking out the first and the last characters. Okay, let me show you the code very quickly. Okay. Okay, let's now see that. Okay, so this is how, conceptually how you do it. Empty string, simply just true. If you got string of length 1, also return true. And now, if the string has a length larger than equal to 2, what do? You simply do the following. You say that first and last character must match, and also the rest is also a palindrome. So this is exactly a recursive call, right? Let's see how you can do that in Java. Okay. Now, what about its palindrome over here? Let's say we have a word string, and let's see the base case. Oh, first of all, you can see that if the length of the word is simply 0 or 1, that's simply return true. That's a base case, right? You can see, again, the syntax here is not really the issue. As long as you can get the idea sorted out, the rest is not difficult. Now, get the first character here, get the second character here, compare them. So now the way I'm going to do it is as follows. You can see that return if the first character is equal to the last character. And then I got ampersand here. Remember the short circuit effect we talked about. If we got ampersand, we only evaluate the right-hand side if the left-hand side is true. If the left-hand side is false, what does that mean? That means the first and last characters are not the same. Then we don't bother to make any further recursive call. Okay, that's what it means. Okay. So now here we say that the first and last character are the same, and the middle part. And how do we retrieve the middle? We simply say middle is the word that's substring from 1 until the second last character, right? And then we say that that's also palindrome. You can see that the middle over here is a strictly smaller problem. Why is that strictly smaller? That's simply the original string taken out front and the end characters. So it's strictly smaller. Any questions? Questions? Are we okay? Oh, not yet. Oh, Sammy, why are you packing up? We're not done yet. You're staying over. Are you sure? Yeah. Okay, very good. It's okay. Feel free to leave if you want to. No worries. Okay, no pressure. Okay, now I want to just talk about one more. Okay, so we can leave our life easier for Tuesday very quickly. Okay, how do you do the reverse of a string? We just talked on Tuesday how you can do the reverse of a string, right? Using a stack. Now the reverse of a string, how would you do it? Okay, Let's try that, okay? Now, I'll just tell you what the idea is. The idea is very simple. Okay? Sammy, don't worry, we're almost done. Okay, now, let's see, how do I do, let's say A, B, C, D. I want to take the reverse of this. Okay? Let's say, I'll give you an idea, don't worry. Since I know the solution, so it's easier for me to tell you, right? Let's say this is input. What's the output? D, C, B, A. Okay? Now, somehow your recursive solution should somehow combine them in a way, right? You want to draw some connection between them. Before I get here, what are the base cases? What's the reverse? What if the string is empty? Reverse of empty is what? Empty. If I got reverse, one character, itself, just itself. Okay, very good. These are the base cases. Now, let me give you visual hints. I'm pretty sure all of you will be clever enough to figure out. I'll give you visual hints. What does that mean? If I got something like that, let's say the input, which has the first character, blue, and also the rest of the string, orange. How can I somehow make a recursive call and combine that into the ultimate solution? So now let's say that the A there is guaranteed to be the last character in the final string, guaranteed. And then what about the orange part? What are the connection between the two oranges? Orange part. It's a reverse of that, right? So which means, now let's be a little bit more explicit over here. So this one here is simply the reverse of B, C, and D combined with the first character. Now it becomes the last. That's the insight. Any question about this insight here? Okay? You can also do it the other way. That's a very good question. Let me just draw that very quickly, and then we're almost done, 1 minute. If you got A, B, C, D, and also D, C, B, A over here, you can either say A, B, C, and then A, B, C over here, right? And over here, you can say that, right? So that means the last character should always be the first in the reverse, okay? Now, the rest is really easy. We can go over that. Again, I'll just show you very quickly the code. You can see the reverse is simply, if it's empty, return itself. If it is 1, and then you will just return itself. And then you will just simply get a tail. Tail simply means everything but the first. Okay? And then you can now get a reverse of the tail. And after that, you can simply get a head, which is the first character, and then combine them in the reverse order, right? You can simply reverse of the tail plus the head. Okay, that's exactly what I illustrated. Okay, we're done. Now, if you got any question about the preparation exercise, send me an email or come to my office hour on Monday. Okay?